27, we're going to talk about color. Now, the color of light that you see is directly related to its frequency. If we go back and we look at that part of the electromagnetic spectrum that represents visible light, we find that we see the colors. They go red, orange, yellow, green, blue, violet. The lowest frequency and the longest wavelength is down here at red light. Red light can have a frequency as low as 4 times 10 to the 14th hertz. That's about 750 nanometers. Or we can go all the way up to this high end. Violet light has a frequency of about 7.5 times 10 to the 14th hertz, or wavelength of about 400 nanometers. This is the highest frequency, shortest wavelength. If you do V equals F lambda here, you're going to get the speed of light, 3 times 10 to the 8th meters per second. Same thing here. If you multiply those together, you get 3 times 10 to the 8th meters per second. As the frequency increases, we see this wavelength getting smaller and smaller. The light from the sun, white light, actually has all of the colors in it. Anytime we mix all the different frequencies of visible light, we get white light. There's actually, if you look in your textbook and in the PowerPoint, you'll see a radiation graph that will show you we actually get most of our light from the sun in this middle range. We get the least amount over here in the blue-violet. So here in the green, yellow, green, that's also where human eyes actually see the best. So let's think about why do we see different colors. It helps if we understand a little bit about the human eye. The human eye has 3 different types of cones, and those cones detect 3 what we call primary colors of light. And those primary colors of light are red, green, and blue. Let me make a diagram with red, green, and blue. There's blue light, green light, and red light. Now obviously, blue light looks to the human eye like blue, and red light looks like red, and green light looks green. These are our primary colors of light. This is different than probably what you learned if you were taking an art class where they talked about mixing paints and primary pigments. If we add up those 3 colors, something really interesting happens. Right here in the middle where they overlap, we get white. If you add blue light, green light, and red light in equal intensities, you will get white light. It's important to think when you add different colors of light, what you get is even lighter than what you started with. If you add blue and red, if we were talking about pigments, we'd expect a dark purple. But we're not doing pigments, we're adding light. We get magenta. Magenta is a pale, purpley pink. So I can make the word magenta fit. It's real pretty, but it's light. It's a light pinkish purpley color. If we mix green and blue, we get a very pale aqua called cyan. And the one that was always sort of the most remarkable to me was the fact that I don't have a yellow marker, but if we mix red light and green light, the result is yellow. Okay, let's stop and think about this. We're going to leave that up there. Suppose white light is shining on a red flower. Let's draw a picture. Got a red flower. There it is. Lots of red petals. Green leaves. So why does the petals appear red? Why do the leaves appear green? If you shine white light on something, you're shining all the colors from the sun, the whole color spectrum. What happens is when something looks red after you shine this white light on it, this will reflect red. And it will absorb all of the other colors. What colors are absorbed depend on the individual molecules and how they react to different frequencies. But generally, if you have light with frequencies near the resonant frequency of the molecules or the atoms, that starts those atoms vibrating, and they actually increase their energy and become hotter. They absorb that energy. Frequencies of light that are far from those resonant frequencies will not be absorbed. They'll be re-emitted. We usually think of re-emitting light as reflecting light. So, since we don't have a transparent object that will actually transmit light, one of two things will happen. It will absorb colors that are not red. It will reflect red. That same light shining, that same white light that contains all the colors, when it shines on the leaves, reflects green. And it absorbs all of the other colors besides green. So if I'm standing here in this pink shirt, the frequencies that combine together to make something look pink are being reflected. Other frequencies of light are being absorbed. If you look at something and it appears to be white, and white light is shining on it, then it's reflecting all of the colors of light. It's reflecting blue, green, red, and that combination looks white. Now, things can look different if you shine different colors. It's easy with white light. With white light, you know a green shirt reflects green. It absorbs the other colors. In particular, absorbs blue and red. Or if you have a yellow shirt, it reflects yellow. Well, look at this. Yellow is a mixture of red and green light. So when something looks yellow, it's probably not just reflecting the yellow frequencies, but also red and green frequencies. Okay. It's absorbing, however, look at what's the opposite of yellow over here. It's absorbing all the blue light, so it doesn't reflect any of the blue light. Okay. If something looks to be red, you know it's reflecting red. It's absorbing blue and green, these other colors. What happens though if we shine something that's not white light? Well, if I shine red light on this combination right here, the flower is going to look red because it will reflect red. But if I shine red light here, there's no light to reflect. These petals in this stem are designed to reflect green light. If there's no green light, they will appear black. So if I shine red light coming in on this flower, only red light, the flower will reflect the red light. This will absorb the red light. And it will actually appear black. If you're wearing a black t-shirt, it's absorbing all of the colors and only a minimal amount of light is being reflected. So it makes it appear black. Okay? If you're wearing a white shirt, it's reflecting all of the colors. Okay? That's one of the reasons that a black shirt is hotter to wear in the summer than a white shirt. The black shirt absorbs that energy from the sun, that visible light, and literally becomes hotter, whereas a white shirt will reflect all of those colors. So, the color you see is what's being reflected. Any other colors are obviously being absorbed. Okay. Now let's make sure we understand what happens when we add light. I'm just going to get 3 colors. No, I'm just going to use 1 color. If I add all 3 primary colors, red plus blue plus green, it's going to look white. That means all 3 of those types of cones in your eyes are being stimulated, and it looks white. If I only add red and blue, I get magenta, that pale pink color. If I add blue and green, I get cyan. That's that very light aqua color, pale blue-green. And if I add green and red, I get yellow. That's almost the most surprising because we've all played around with paint when we were little. And if we were talking about paint, green paint plus red paint would make an awful muddy brown color. But green light plus red light can make yellow. Now if we put a little bit more red in it, it may look orangier. Or if I put a little more green in it, it may be a greener shade of yellow. Okay. There's a whole lot more colors than just these 6, but we create them all by using varying intensities of different frequencies. A lot of blue, just a tiny bit of green, a little bit of yellow frequency, and we can create all of the different colors. Okay. These are the primary colors of light, red, blue, and green. There's something else we want to talk about, and that's called complementary colors. Complementary colors add to make white. Now, the primary colors are red, blue, and green. The secondary colors of light are cyan, magenta, and yellow. Those are our secondary colors. All right, complementary colors add to make white. If you memorize this diagram, it really can help you with some of the questions about adding light. But basically, I have to think blue, whoops, I wrote an R. Blue plus what is going to equal white? Well, I know blue plus red plus green. Well, red and green make yellow. So blue plus yellow will equal white. Those are complementary colors. If I pick green as my primary color, what secondary color would I need? Well, I'd need blue and red. I'd need magenta. That will also make white. If I start with red as my primary color, I would need to add cyan. I need the blue plus the green. And again, I'm going to get white. So complementary colors are colors that add to make white. One primary color of light plus one secondary color of light. Okay. Second, let's look now at pigments. When we're talking about light, we call those the additive primary colors because we can add them up and get white. When we talk about pigments, we talk about subtractive color because pigments literally absorb different colors of light. They subtract it so that you see less and less. If you add all the pigments together, you always end up with black. So if we're talking about pigments, these are often called the subtractive primary colors. Now, let's stop and think for a minute. When we were adding light, as we added more and more different colors of light, we always got something lighter. If we added all the colors of light, we could create white. Pigments are exactly the opposite. If we mix all the colors of pigments together, we actually get black. So the primary pigments are actually very light colors. The primary pigments are magenta, cyan, and yellow. If I mix all three of those, it will make black. But I can make any color of dye or paint that I want using those colors. If you look at a color photograph, it's made up with a mixture of those three colors. If you go and buy a color ink cartridge, that color ink cartridge is going to contain magenta, cyan, and yellow. And your printer can use those colors to make all of them. It could even use them to create black, but it would use so much ink that they give you a separate black printer cartridge. If I were to make a diagram, it would look like this. I'm going to do the different colors. You'll have to magenta, cyan, yellow. If I mix all three, I get black. If I only mix cyan, that blue-green color, and yellow, I get green. If I mix magenta and yellow, I get red. And finally, if I mix cyan and magenta, I can create blue. So interestingly, if we're doing pigments, it's almost in reverse. The primary pigments are the secondary colors of light. The secondary colors for pigments are that red, blue, and green. And then, of course, if you add all three together, you get black. It helps you get this right if you remember that as you're starting with light-colored pigments, and as you add more, they absorb more and more of the light, because that's exactly what a pigment does. Something that's a blue dye or a blue pigment reflects blue light, but it's absorbing all the greens and all the reds. If something appears to be a yellow pigment, it's reflecting red light and green light and yellow light, but it's absorbing all that blue. Okay. It takes a little practice, but I don't think you'll have that much trouble figuring it out. Now, there are some things that we may be curious about why they appear to be colored, like the sky. It looks like air should be clear, and air really is kind of transparent if you're talking about a vacuum. Same thing with water. Water looks like it should be clear, but it's actually not always clear. Clouds are made up of water droplets, and yet clouds appear to be white. So what's going on, and how come things have those certain colors? Well, one of the things we go back to is this idea of resonance. We talked about it with waves. If you vibrate something at just the right frequency, it will begin to vibrate. In other words, if I send out a wave and I have a tuning fork at that frequency, that tuning fork will start to vibrate, and that tuning fork will send that sound wave out in all directions. That sending it out in all directions is called scattering. Okay? If we want to talk about the blue sky, the atmosphere, because remember it's not really empty space up there, has a resonant frequency that's in the violet range. It's up at the, even the ultraviolet range, it's up there at the high end of the color spectrum. What that means, since it's at the high end of the color spectrum, that it will vibrate those molecules that make up the air. They're resonant at that frequency. They'll absorb and then re-emit those colors. So what we know is that the atmosphere scatters violet and blue much, much more than it scatters the lower frequency colors, the reds, the orange, the yellows, the green. The result of that scattering at that blue light is that the sky appears blue. Now, remember the sun makes white light? But when we look at the sun, if you've ever looked at a child's artwork, we all think of the sun as being yellow, or even sometimes orange or red, depending on the time of day. Why does the sun look yellow if it's got white light? Well, the complementary color to blue is yellow. So since the atmosphere scatters that blue light, giving that sky the blue appearance, the light that actually reaches us from the sun has a yellow cast to it. It's missing some of the blue light. Okay, so let's just draw a picture of the Earth just for a minute. So I think the Earth should be green for this picture. So if we have the Earth here, if we have the atmosphere up here, when the sun is high in the sky, it's going to appear, if it's directly over us, it's going to look yellow. And I don't have a yellow marker. And that sky all around during the middle of the day is going to look blue because it scatters out the blue light. But at sunset, let's think about this. At sunset, the sky is not directly over. So I'm going to draw this even bigger. If we're here on Earth, at sunset, the sun is way down here. And the sun's light that reaches us has to travel through all of this atmosphere. There's a lot of atmosphere going on. Well, what happens is, remember, blue light scatters first. And then, well, violet, but we don't really see violet very well. Violet, then blue, then green, then yellow. By the time this light reaches us up here at sunset, the only wavelength that can actually penetrate that much atmosphere is going to be red. It doesn't have to, if you think that there being this much atmosphere, just drawing that. Well, here, when it's directly overhead, it just has to go through a little bit of atmosphere to reach us. But when it's way over here, it has to go through a whole lot of atmosphere to reach us. This is just enough to scatter out the blue. But by the time it makes this, the light rays make this really long trip, the sunlight has pretty much scattered out all the different colors in the spectrum except for the red. So at sunset, because those rays travel through such a large part of the atmosphere, it tends to look red. Now, why are clouds white? Well, small particles like nitrogen and oxygen molecules scatter out blue light. That's what the atmosphere does. Larger particles would scatter out green or yellow light. Even larger particles might scatter out orange and red. Well, clouds have water droplets, and some of them are very small and will scatter out the blues and violets. Some are kind of medium sized. They'll scatter out the greens and the yellows. And then some are really fairly large and tend to scatter out the red and orange. So the result is they're scattering all of the different frequencies of visible light equally. Well, if you're scattering all the frequencies of visible light equally, you're going to see white because you're getting all of the colors. Okay, the last one I think we wanted to talk about was the water. Well, just like the atmosphere has a resonant frequency that's in that violet range, so it scatters out the violet and the blue and makes the sky look blue. Water has a resonant frequency that's kind of in the blue-green range. It's a little lower frequency. So it tends to scatter blues and greens, and it gives water that really beautiful kind of aqua color. Again, depending on what's in the sky, how much humidity, how much dust, the color of the sky can look lighter or darker. Same thing with water. Depending on what kind of impurities, whether it's salt water or fresh water, the color can be very beautiful. If you've been to places like some of the Florida beaches, it's absolutely beautiful. Or if you've been to Galveston, it can be kind of muddy brown looking. Really depends on what, but clear water, like swimming pool water, tends to have that aqua blue color. Okay, I think that's all I want to talk about today about color. I think color is really interesting. If you have questions, shoot me an email.